Hi guys, it's Hannah here, and today Sahana and I will be explaining the hybridization of ammonium. First, we will begin by making a Lewis dot diagram for ammonium. To help us find the number of bonds to use, we will use the have-need method. First, we'll calculate how much NH4 needs to be stable. Nitrogen needs 8 electrons to be stable, and hydrogen needs 2 to be stable, but there's also 4 hydrogens, so you must multiply the 2 electrons by the 4 hydrogens to get the total sum of 16 electrons. Next, we need to calculate what NH4 already has. On the periodic table, nitrogen is in group 5, meaning it has 5 outer valence electrons, and hydrogen is in group 1, meaning it has 1 outer valence electron. So now it will be 5 plus 1 times the 4 hydrogens, and ammonium is positively charged by 1 electron, meaning it will lose 1 electron. Now let's put it back in the equation. So it's 5 plus 1 times 4 minus 1, which equals 8. Now we substitute it into the formula, need minus have divided by 2, which is 16 minus 8 divided by 2, which then will get 8 divided by 2, which our final answer will be 4. And that is the number of bonds our Lewis structure will be having. Now that we have more information, now we can draw the Lewis dot diagram. Hydrogen has 5 outer valence electrons, so we'll draw them all out around it. We also know that NH4 is positively charged by 1, meaning it will lose 1 electron. So we must remove one of the electrons that we've already drawn. And hydrogen has 1 outer valence electron, and we have 4 hydrogens, so each hydrogen gets 1 electron. Now to check if my diagram is correct. So nitrogen has 8 valence electrons, and as you can see, there are 8 valence electrons for nitrogen, and hydrogen has 2 valence electrons, and each of my hydrogen has 2 valence electrons. Therefore, my NH4 is stable. However, I'm not done yet. My central atom is surrounded by 4 bonding pairs, meaning it has a tetrahedral shape. So first let's draw the 2D shape. As which you can see, there are 4 single bonds, and it is positively charged by 1. Tetrahedrals have 3D shapes, meaning that NH4 can be drawn into a 3D shape. So first I will draw all the surrounding hydrogens. Next we'll draw the bonds. The first 2 will be looking normal. The third hydrogen will have a triangle indicating that the hydrogen is coming out of the paper. Next, we'll have dotted lines indicating that the hydrogen is pointing into the paper. And we must include the brackets and the charge. And lastly, we will show the angle. And for tetrahedrals, it is always 109.5 degrees. And that's our completed Lewis dot diagram.
Hey guys, now it's Sahana and I'm going to be cutting in to explain the rest of the hybridization process. But before that, let's discuss a little bit about the intramolecular forces of ammonium. There's 2 types of chemical bonding, which are ionic and covalent. In ammonium's case, it's covalent bonding. Covalent bonds are formed when 2 atoms share pairs of electrons between one another. These electrons are not always shared equally, however, in ammonium's case, they are. This shows that ammonium has nonpolar covalent bonds. The 4th hydrogen in the compound is also connected to a coordinate bond, which can be called a dative bond as well. Ammonium has a tetrahedral shape to it. This means all NH bonds are arranged symmetrically over the nitrogen atom. Nitrogen and hydrogen also differ in their electronegativity. Nitrogen has an electronegativity of 3.04 and hydrogen has 2.20. This causes a difference of 0.84, which determines that ammonium's individual bonds are polar bonds. Therefore, even though ammonium as a whole is a nonpolar ion, its individual bonds are polar. This brings us to discuss 2 physical properties of ammonium that would exist based on our understanding of the intramolecular forces. Intramolecular forces are the forces that hold atoms together within a molecule. First, it has a high melting point. The individual polar bonds create such strong forces of attraction. It will be much harder and it will take much more energy to undergo the process, which shows that ammonium relatively has a high melting point. This would be the same with ammonium's boiling point as well. To clarify, it will be high. A second physical property is solubility. Ammonium has a high solubility, specifically in water. Ammonium has hydrogen atoms that are capable of hydrogen bonding. The capability of hydrogen bonding determines that ammonium is polar. Therefore, it will be soluble in a polar solvent, such as water. Now moving back to the hybridization process. To continue, let's first figure out the electron configuration. The central atom of the compound is the element used to determine the electron configuration. In this case, the element is nitrogen. To start off, we write 1s2. 1s2 because hydrogen and helium both belong to the s orbital, which is in the first row. 2 comes at the end because 2 elements are in this group. Next, we write 2s2 because lithium and beryllium both belong to the s orbital, as well as they're in the second row. The next step is the p orbital, with 6 elements in this group. Nitrogen is a third element, and so we write down 2p3. 2 because it's the second row, p because it's in the p orbital, and 3 at the end because nitrogen is the third element in the group. Next, we will be writing the condensed version, and in other words, the shorthand version. We first start off with writing down the noble gas that is prior to the central atom in brackets. In this case, the central atom is nitrogen, and the noble gas prior to it is helium. So we write He, short for helium, in brackets. Then, instead of starting from the beginning and writing 1s, we continue from where helium is located. Helium is located at 1s2, therefore we skip that and we finish off writing it with 2s2 and 2p3. Writing down the full electron configuration can help figure out your next steps as it just did for us. Now that we have the condensed electron configuration, we can move along to our next step, the condensed energy diagram. First, make a chart like this with PE written on the left and have a dotted line separating your different orbitals. Your next step is to add the noble gas into your diagram. You are simply going to add it at the very bottom of the s orbital column. Keep the element symbol in brackets as well. Next, we need to add in 2s2. S orbitals are single and they may hold 2 electrons each, so draw one line in the s column and write 2s under it. Next, let's add in 2p3. P orbitals are groups of 3, so this maximizes our electron limit to 6. Draw 3 lines in the P column this time and write 2p under it. Now it's actually time to fill in the electrons. This is done by drawing half-headed arrows. Since 2s has 2 electrons and that is the maximum limit, we simply draw 2 half-headed arrows. Now, for 2p3, we could have 6 electrons drawn as 6 is the maximum limit, but nitrogen only needs 3 electrons. Don't make a mistake of drawing 2 arrows on one line together. The right way is to draw 1 electron each on every line from left to right before going back to add a second electron on the lines. Now moving along to the actual hybridization process. Draw another chart similar to the first one. Ammonium has 4 single bonds and it loses 1 electron. There's no lone pairs and there's no coordinate covalent bonds either. Write down that there's 4 single bonds in between both diagrams to make things more clear. Since there's 4 bonds, there must be 4 orbitals in the new diagram. We must take the orbitals from the first diagram and move them to the second. Since there's only 1 s orbital in the first diagram, we can only draw 1 in the second diagram. Then there's 3 p orbitals, which we add to the second diagram as well, and this perfectly leaves us with 4 orbitals in total. Counting back on how many electrons we have, there are 5. However, we must remember that ammonium loses an electron, so 5 minus 1 equals 4. At last, this leaves us with 4 electrons. Therefore, we add 4 electrons by drawing half-headed arrows again. We draw an electron on each line, and we don't need to go back and draw seconds since that isn't necessary. Now, to name it, we don't separate them by letters like we did in the first diagram. Instead, we join them together. Since both s and p orbitals are from row 2, we keep the number 2. Then, we add on the letters. Since we only took 1 s orbital, we write down s. We don't need to write number 1 as a superscript, and so we move on to p. We took 3 p orbitals, and so we add the letter p with the superscript 3. This leaves us with 2sp3, and here is our final hybridization diagram of ammonium. This is the end of mine and Hannah's little lesson of the hybridization of ammonium. Thank you for listening, and we hope you got to take away some valuable information from this video. See you next time.